Bismillahirrahmanirrahim. Assalamu alaikum, dear student. My name is Dr. Muhammad Adnan Asghar, and we are discussing about the characterization of pharmaceutical materials by thermal analysis. So far, we have discussed in this series of lecture, we have discussed some of the crystallinity nature of the pharmaceutical material by using different thermal analysis techniques. The most renowned one was the modulated diffraction scanning calorimetry, and now we are going to discuss in crystallinity subject a polymorphism. Uh, this is actually quite important subject to learn about the polymorphism and even for the detection of different polymorphs in any compound by using thermal analysis techniques. Some materials even can exist in multiple crystal forms, which is called polymorphs. They have same chemical structure but a different crystalline structure, which can result in significant differences in physical properties such as solubility, bioavailability, and storage stability. The most stable form typically has the lowest dissolution rate and may not be the ideal form for a particular application. For all of these reasons, plus others associated with the development and manufacture of efficient and effective drug delivery systems, it is important to know if a specific compound can and does exist in different polymorphic forms. Diffraction scanning calorimetry is believed to be the most widely used analytical technique for measuring crystallinity and crystalline polymorphs. However, the results are often misinterpreted by some users who fail to realize that the sample may be changing as it is heated. The fact that it can change means that kinetic processes are involved. These include crystallization of amorphous material and even conversion of less stable polymorphic forms into the more stable forms that usually melt at higher temperatures. Two techniques that can be used to better understand what is happening to the sample as it is heated are modulated diffraction scanning calorimetry and multiple heating rate diffraction scanning calorimetry. The benefit of modulated diffraction scanning calorimetry can be seen in the comparison of some of the drugs. For example, in this structure we will explain the different polymorph microsphere with approximately 30% drug. The standard diffraction scanning calorimetry is actually gives this kind of peak. This is actually the upper one peak is given by the standard diffraction scanning calorimetry. The standard was it is actually run at a relatively low heating rate of 5 degrees Celsius per Kelvin uh, to optimize resolution of multiple transitions. It is somehow nearly impossible to interpret the exact data, while in the lower case uh, is actually the lower one is actually belong to the modulated diffraction scanning calorimetry, and this data on the same material. The reversing heat flow signals show a very clear glass transition at about 30 degrees Celsius, which is very clear in this diagram, and two melting peaks at about 170 125 degrees Celsius and 175 degrees Celsius. Since melting happens after the cold crystallization, exothermic and total signal, the sample was primarily amorphous. Other transitions that complicate the total signal of diffraction scanning calorimetry include enthalpic recovery at the end of glass transition, evaporation of 2% volatile. This could be done by using TGA, thermogravimetric analysis, and crystallization of amorphous drug just above 100 degree Celsius. The benefit of multiple heating rays uh, will be illustrated on several drugs. The first is sulfonamide, which is reported to have three polymorphic forms. These are easily detected as shown in this figure. Uh, Actually, it is a comparison of data created for different polymorphs of sulfonamides. Note that heating rate has very little effect on the number and shape of the melting peaks, except for slight broadening of large peak at near the 165 degrees Celsius. Here we can see that. This means that each polymorphic form is relatively stable and actually does not transform from one form to another during that particular experiment. It is very easy to characterize the relative amount of each form in this kind of sample. In this diagram, we can clearly observe that it's a kind of very little effect on the number and the shapes of melting peaks, except for slightly broadening of large peak at 165 degrees Celsius. So we are unable to actually distinguish of the peaks of different polymers of sulfonilamides. The second sample, which may be which may be discussed with multiple heating rates, is a drug monohydrate. This actually shows that the data at 10 and 1 degree Celsius per minute respectively. Note that both experiments may be performed with hermetic pans, which is actually sealed pans to prevent evaporation of water. The importance of this will be illustrated in next lectures. This shows that the data from uh, 10 degrees Celsius per minute experiment at two sensitivities in order to illustrate some of the fine points. The slight step at leading edge of the melt is not a glass transition. This is actually verified by modulated diffraction scanning calorimetry data, which will heated and cooled over this entire temperature range. In addition, the glass transition of the amorphous drug is near 50 degree Celsius. The baseline actually shift from the beginning to the end of the melt is caused by higher heat capacity of liquid phase as compared to the solid phase. Because of this step, the most accurate way to integrate the peak is with the sigmoidal baseline. The most important information from this scan is that there is only a single melting peak, that is one polymorph. This figure appears to be from a totally different sample than the previous one. However, it is the same material. The huge difference in the results is simply the results of using unsealed versus sealed pan, whereas in previous figure uh, was it is actually was created with sealed hermetic pan, but whereas in this picture we used a hermetic pan with the pinhole in the top. This pinhole actually allows water to escape from the pan, which also called the conversion of the crystalline material into an amorphous form. The amorphous form crystallizes near 120 degrees Celsius and then melted near 174 degrees Celsius. In a sealed pan with water, which is about 5% present, the sample showed very little tendency to crystallize after it had melted. Uh, next in this picture, it is actually the comparison of the last pictures, which were both run at about 1 degree Celsius per minute with only experiment different being used, the sealed versus unsealed pans. This is actually an important point to be learned from this data on the drug monohydrate. The presence of moisture or solvents can have a significant effect on diffraction scanning calorimetric results. Therefore, always run thermogravimetric experiments on new samples to determine the temperature and amount of weight loss. When it exceeds about 0.5%, always compare the effect of sealed versus unsealed pans on the results. Use the type of pan that provides the most meaningful information on the properties of material. The third and last polymorphic drug to be characterized at multiple heating rates is anhydrous and contain less than 0.05 volatiles. Therefore, it run in standard crimped aluminum pans which are not completely sealed. And this example may mm, illustrates the value of using multiple heating rates to characterize the ability of the drug to convert from one polymorphic form to another one. In general, start if we start with the heating rate of 10 degrees Celsius per minute, if only a single melting peak is detected, then there is probably no need to use other conditions. If multiple peaks or shoulders on major peaks are seen, then a lower heating rate experiment should be performed to see if overlapping peaks can be separated or additional peaks may form. And this figure actually shows the data for the anhydrous during anhydrous drug at about 10 degrees Celsius per minute. There are clearly two peaks, and the data might be integrated with a perpendicular drop from the baseline to try to quantify the amount of each polymorphic form. However, the results would be totally wrong as seen from this figure, which is the same material. This is the same material but heated at only 1 degree Celsius per minute. The last one was heated at 10 degrees Celsius per minute, and we get the structure, we get the data like this. And for the same material, if we just change the heating rate, we will get the data like this one. In this case, there is an additional peak at 175 degrees Celsius. Here we can see it's quite clear, and a very different ratio of peak size for the peaks near 150 degrees Celsius and 155 degrees Celsius and 161 degrees Celsius. In both experiments, the total energy of melting is the same, which is 65 joule per gram, but it is distributed very differently among the various polymorphic crystalline forms. Since this sample change significantly with the lower heating rates, it is necessary to use higher heating rates, which may be 50 to 100 degrees Celsius per minute, to minimize the time and opportunity of one polymorphic form to convert to another polymorphic form. Actually, these two graphs, this graph is actually at the heating rate of 10 degrees Celsius per minute, and we will get the results like this, and these results are quite interpretable. While if the sample is same, the drug is same, but the heating rate is 1 degree Celsius per minute, then the result would be like this one, and it is somehow unable to interpret the data quite visibly. So it means that heating rate of sample is quite important. It would help us to determine the right informations to right applications of any drug or any material, while it can interrupt the data if the scan rate is quite low from the optimum temperature. In this figure shows it actually shows the data at 50 degrees Celsius per minute heating rate with the result from the 1 and 10 degrees Celsius experiment overlaid for the comparison. So this is for the 1 degree Celsius per minute, and this peak is actually for the 10 degrees Celsius per minute, and this is for the 50 degrees Celsius per minute. These are the three different parameters, but the sample is same. At high heating rate, only a single melting peak is seen, which means that there is only one polymorphic form in original sample. Since it begins to melt at 153 degrees Celsius, as also seen in the 1 and 10 degrees Celsius per minute data, the crystal form in the original shape is the lowest temperature polymorphs. It is supposed to be the least stable polymorph. Here we can see that these are the actually sample, these are the heating rates of same sample, but different heating cycles and heating rates. If we performed on the same sample, the results are quite obviously different. One concern at high heating rates is the loss of resolution. So this is a quite disadvantage of the high heating rates. Major benefit of the new modulated diffraction scanning calorimetric technology is the higher resolution, which would be provided by some T4 and heat flow signals, which account for the thermal lags that occur due to the sensors and bands. The higher resolution results often make the difference between the seeing and not seeing a small amount of one polymorph in a mixture of other polymorph. For example, the modulated diffraction scanning calorimetry with traditional one term, the polymorph detected at about, for example, 170 degrees Celsius uh, will be verified to be real by hot stage microscopic results. The lower resolution signal of conventional diffraction scanning calorimetry may not be able to detect it at even high heating rates of 50 degrees Celsius per minute, while lower heating rates would not be used due to the sample changing during the experiment. So, from this picture, it would be quite obvious to learn that at even at high heating rates, only a single melting peak is observed, which means that there is only one polymorphic form in original sample. Since it begins to melt near 153 degrees Celsius, as also seen in different heating rates like 1 degree Celsius per minute and 10 degrees Celsius per minute, we can see that that crystal form in the original sample is the lowest temperature. Uh, the lowest temperature means it would be the least stable polymorphic. So Diffraction scanning calorimetry would help us to determine the different polymorphic structures in one sample by using different heating rates. Even sometime we need to perform the uh, diffraction scanning calorimetry at about 1 degree Celsius per minute, and sometime 10 degrees Celsius, and sometime 50 degrees Celsius. And sometime we also need to perform the modulator diffraction scanning calorimetry at about 100 degrees Celsius per minute for the successful detection of different polymorphic structures in pharmaceutical compound. This is all about this structure lecture. Thank you very much.